Hello and welcome to a new Precalculus video. This is for lesson 11 in Math UC. So today we're talking about the sum and difference identities. What are the sum and difference identities? Well, let me tell you. It turns out that through a complicated process, I imagine, because I haven't actually done it myself, we can find new identities to help us get more exact values for angles than we could before. Because right now, based on what we know, we can do exact values, so square roots and fractions for multiples of 30, multiples of 45, and multiples of 60, which is also multiples of 30, as well as multiples of 90, I guess. All of those things we can get like from a unit circle or by using special right triangles instead of having to use our calculator or trig tables. So wouldn't it be nice if we knew more than just those angles as exact values? And so sum and difference identities are one set that let us do that, and then we'll have another set of identities in lesson 12 that lets us do that. So the idea here is if we can write our angle as a sum of two, or a difference of two angles that we do have special right triangles for, or special values for, then we can fill in the identity and get an exact value. So we're going to be seeing a lot of things that say like sine of a plus b. Okay, so that's saying I have sine of two angles that I'm adding together. So maybe it's that we are going to try to find 75 degrees, sine of 75 degrees. Well, we could rewrite that and say what two angles add up to get 75, preferably using numbers that go with special right triangle angles. So in this case it'd be 30 plus 45. So I wanted to preview with this part because I think when you see the identities here in a second, it's going to make more sense because these identities are kind of weird. Let's take a look. See, they're a little bit, they're kind of like long. They've got these plus or minus signs, which is a little bit, might seem a little bit weird. And that's just because when we write these, we like to do shortcuts because there's already a lot of writing. So if you have an identity sheet that you've been adding to along the way, this is definitely something you should add to your identity sheet. Or if you printed one off, it could be that they're already there. So if you printed one off or your teacher gave you one that already had these identities, make sure you take note of where those are. They could use letters other than A and B. They could have these written out separately instead of having the plus or minus signs. That's an option. But they should look something like this. Now let me explain what the plus or minus thing does, because over here on our left we've got plus and minus symbols on each of these. So that means there's a sum identity, so A plus B. There's a difference identity, A minus B, for each of these. And that basically the only thing that changes, whether if you do A plus B or A minus B on each of these, is that it swaps the sign on the right side. But the way it does this is interesting, to me at least. So if you look at sine of A plus B, or sine of A plus or minus B, and then you look at the right side, it also has a plus or minus. And so what that means is that if you have addition on this side, you're going to have addition on this side. Where that's different is on cosine. Look, our plus and minus sign is actually upside down. That's trying to tell you that if you have cosine of A plus B, that you're actually going to use the minus on this side. They are going to have opposite signs. And just to make that even more tricky, tangent has a plus or minus and an upside down plus or minus sign on the right side. And so that means that when we do tangent of A plus B, we look at the top and put a plus, and we look at the bottom here and we'd put a minus. So we're going to walk through each of these. We're going to do one of each, a sine, a cosine, and a tangent, and work through this. There are going to be probably a few proofs or verifying sorts of situations along the way, but it's not going to be quite as proof heavy as before, because here one of the big advantages of sum and difference identities is it helps us actually calculate angles, or sine and cosine and tangent values of angles that we weren't able to before without our calculator. And so this is really going to come down to like what angles can we get by adding or subtracting 30, 45, 60, 90, and all of their multiples that you know, if we add or subtract and get something that we haven't been able to find with a special right triangle before, then aha, you may have stumbled across one that we're going to see a lot. So let's take a look. Example 1, evaluate by using familiar angles and the sum and difference identities without a calculator or the trig tables. State the formula before solving, and there may be more than one way to do some of these, especially because subtraction, well, I guess with both of the, no, with subtraction makes it to where you could use a whole bunch of different angles. Because if you were to look at a unit circle, for instance, there are so many pairs of angles that are 15 degrees apart that we could pick so many different ways of doing this. The easiest thing to do, though, would be to pick small angles. To get 15 degrees using angles we already know stuff about, I'd pick 30 and 45 and say, all right, sine of 15 degrees is the same as sine of 45 degrees minus 30 degrees. Okay, now think about it. Do you agree with that? That 45 minus 30 is 15, and that we can make that exchange, right? We can make that substitution. Hopefully you do. I am going to, since we've decided to do 45 minus 30, since I've decided, I'm going to write down the sine identity, just so it's handy here. I personally don't really care if you write it. Do pay attention to where the A's and B's are, because that does matter. Okay, so sine A cosine B minus cosine A sine B. It's kind of cool how this works. I haven't actually tried to prove one of these before, but it's still neat that it works out this way. These are also going to end up feeling really repetitive after you've done a few of them. Just so you know. You know, I know, we all know that's going to happen. So in this case, our A is 45 and our B is 30. The minus sign is a part of this formula, so we're not going to need to make B negative 30. We can make it just be regular 30. So sine A, so sine 45, times cosine of B, so that's 30, minus cosine of A, so that's 45, and then sine of B. Now we've got two ways to figure out sine and cosine of special right triangle angles. One way is to think about our special right triangles. That's a good way to do it. This does not really look like a 30, 60, 90 triangle, but I didn't at first think it looked like a 45, 45, 90 either. So either we draw or picture in our head our special right triangles, or we use our unit circle to figure these out. And since we're just doing sine and cosine on this one, the unit circle is helpful because it already has them rationalized and stuff. So sine of 45 is opposite over hypotenuse, or the y value on the unit circle. So that's 1 over the square root of 2, or as it's rationalized, square root of 2 over 2. Okay, cosine of 30 is adjacent over hypotenuse, so that's square root of 3 over 2. Cosine of 45 is the same as sine of 45. Cosine and sine of 45 are always going to be the same, so that's going to be square root of 2 over 2. Sine of 30 is opposite over hypotenuse, so that's 1/2. So just to make sure we understand how this whole fraction radical stuff works, we can multiply together things that are under a square root like this, so square root of 2 times square root of 3 gives us square root of 6. These 2's can multiply together and get 4. We can't simplify square root of 6 over 4, like you can't take a 2 out of each of those because the 6 is protected by the square root, or at least that's how I like to think of it. Square root of 2 times 1 is just square root of 2. 2 times 2 is 4, and so we have common denominators here. I'd say that probably most math books or math teachers would say that this is our best way of writing this, is that you'd write it together as one fraction. We can't do square root of 6 minus square root of 2. That's not how square roots work, just to remind you. If we had two square roots that had the same number inside, we could add or subtract them like they're like terms, but that's not happening here. So we can't, and we can't change either one of them into something else. So that's our answer. Like I said, this is going to seem really repetitive, so as you're going along doing these, you might notice that, and maybe you feel like it's frustrating. Maybe you're like, well, it's kind of nice that I can pretty reliably know that I got the right answer. Let's look at cosine of 75 degrees. So what are two angles that we could either add together to get 75 or subtract to get 75? I guess I gave this away at the beginning, that we could use 30 plus 45. So that gives us what our A and our B value are. I'm going to write down the cosine identity. Cosine is different because the cosines are together, and then it's also different because it changes signs here. If it's plus on the left, it's minus on the right. Remember, that's what the upside down plus or minus means. And then the signs are together. So let's fill this in. We're going to do cosine 30, cosine 45, minus sine of 30, cosine 45. And if you drew the triangles on the last one, you can use those, or if you're using your unit circle, you can use those, whatever it takes here. I'm going to try to visualize them in my head. So cosine of 30 is square root of 3 over 2. Cosine of 45 is square root of 2 over 2. Sine of 30 is 1/2. And cosine of 45 is square root of 2 over 2. I'm not a marshmallow, you're a marshmallow. No, you're a marshmallow. It's raining marshmallows. How silly. So if we look at this, it's actually really similar to the previous problem. Square root of 3 times square root of 2 is square root of 6 over 4 minus square root of 2 over 4. Wait, it's not just similar, it's actually the exact same thing. I actually realized that at the end of the last problem, because I was going to point out that one of the reasons we're getting similar answers, right, is because we already knew that we already have an identity that says that sine 15 degrees equals cosine of 90 minus 15, and we've already seen evidence of that as well. So that's one of the reasons why we're going to end up with super similar answers. The other is just because we're going to keep using these same fractions in kind of a variety of orders. So just keep that in mind as we go along through these. Let's do tangent, and let's make this a little more interesting by using 165. So we're looking either for things that add to get 165 or subtract to get 165, and I'm going to be honest, I'm more likely to probably think of things that add, I want to say. So looking at a unit circle might help, because then you can see all the different angles, because 60 and 45 aren't big enough. We need a bigger angle. You can't do 90 and 45, but we're getting closer. 120 and 45 would work. So I essentially was visualizing the unit circle in my head. So we've got plus, so we're going to use the tangent of a plus b formula. On top, we add them, tan a plus tan b, and on bottom we do 1 minus the two of them multiplied together, like this. At no point, I'll kind of re-say this maybe, or maybe for the first time say, like, at no point along the way here should we be grabbing our calculator to try to do this, because the calculator is going to give us a decimal, and that's not what we want. So if I fill this in, 120 is A, 45 is B. By the way, it wouldn't matter which order I put it in. Like, it would matter for how I fill in the right side, but it wouldn't, I should still end up with the same answer. Alright, so let's fill this in. So we've got on top tangent of 120 plus tangent of 45 over 1 minus tan 120 times tan 45. Now, tangent of 45 is a really nice number. Tangent of 45 is 1, because you do opposite over adjacent of the two sides of your 45, 45, 90 triangle, which are the same. So I know that. Well, let's think about what 120 is. So this is 120. It gives us a reference angle here of 60. So this is square root of 3, negative 1, and 2. So opposite over adjacent here, this is negative square root of 3. I want to make a comment about this in just a second after I fill it in. So tan 120 is negative square root of 3, tan 45 is 1, 1 minus, this is negative square root of 3, and this is 1. So the alternative to this, if we instead were taking tangent of a 30-degree reference angle, that would make us have 1 over square root of 3 or some version of that, and then we'd rationalize that. It actually kind of adds a bit of complicatedness that we didn't see here. It puts fractions on top of fractions, so you might need some help walking through that the first time that happens to you. But what can we do here? The top, I guess we can switch this around. We've got minus and minus square root of 3 and 1, so that's going to end up being plus square root of 3 on bottom, like this. And then, generally speaking, a lot of times we will rationalize the denominator to get the square root off the bottom, and to do that in this case, we'd multiply by 1 minus the square root of 3. We multiply by the same thing that's on bottom right now, but with the opposite sign in the middle. It just so happens to be what's on top. And then we like foil this out. So this is ending up to be a long process. So on top we do 1 times 1 and get 1. 1 times negative square root of 3 and get negative square root of 3. Negative square root of 3 times 1 is also negative square root of 3. Negative square root of 3 times negative square root of 3 is plus square root of 9, which is just 3. And then on bottom, what should happen is the outer and inner terms when we FOIL should cancel, because that gets rid of the square root. So 1 times 1 is 1. 1 times negative square root of 3 is negative square root of 3. Square root of 3 times 1 is positive square root of 3. See how those canceled? And then square root of 3 times negative square root of 3 is negative 3. So on top is 1 plus 3, which is 4. Negative square root of 3 minus square root of 3. Those are like terms, so we can combine those to be negative 2 square roots of 3. 1 minus 3 is negative 2. Now, the way this works, which it may have been a while since you've done this, is if all three of these numbers are divisible by the same thing, it's actually a better way of thinking of it is thinking about splitting this up into two fractions. And the reason to do that is because it does divide. That would give us negative 2 plus the square root of 3. So that's kind of a long process, and I actually don't know. I haven't double checked to see if that's what math you see, if that's what the solutions want you to go all the way to. But that's definitely something that we should check on. And it may be that you need some help getting through this the first couple of times. But again, the bright side or terrible side of this is that we should end up with similar things over and over again. So just because you didn't understand how to do it the first time or the second time or even the third time maybe, hopefully by the time you've repeated it enough, you'll start remembering the steps and it'll make more sense. So the kind of things we typically will verify or prove with these identities are, in some ways I feel like simpler. They don't usually put it in with other things to make super complicated ones. So we would say this is cosine of a minus b, and we can use that identity to see if we can simplify it down to just be sine theta, basically. So let's see, cosine of a minus b is cosine a cosine b plus sine a sine b. So we're going to replace the a's with 90 and the b's with thetas. So cosine of 90 degrees cosine of theta plus sine of 90 degrees sine of theta. And so our hope here is that things are going to go away basically because we want it to just be sine theta. So remember how 90 degrees works, that's up here. The easiest thing to do is to think about our unit circle, which has the point 0, 1, and to remember that the x value is cosine and the y value is sine. The slightly less easy way is to pretend like you're making a triangle, even though you can't really make a triangle, and then work it out from there. But cosine of 90 degrees according to the unit circle, and any other way you do it correctly, is 0. And that's helpful because 0 times cosine theta is going to be 0. Sine of 90, though, is 1. And so 1 times sine is 1 sine, or just sine. So you can see now 0 plus sine theta is sine theta. And each of these, I think, should work out pretty similarly. Obviously, the tangent one might be a little bit tricky to work out, but I think sine and cosine, and even maybe secant and cosecant shouldn't be as bad. But that's how you go through that process. Thanks so much for watching. If you haven't already, please be sure to subscribe. Go ahead and hit like on the video if you liked it. I'm not saying that you liked the math necessarily, but if you like me, or you like the fact that you found this video because it was helpful, and I'll see you in the next video. Bye.